Some beginnings kick the door in, others leave a note on the sill and disappear into the night. The universe began like the note, not because it lacked force, it didn't, but because we meet it through what it left behind, a background glow that never went out. The first simple nuclei, counted and recounted, subtle patterns that stayed consistent while the whole cosmos grew larger around them. Good evening, my name is Madeline Rowe, and this is the science of the Big Bang and early universe for sleep. And if you enjoy these calm, evidence-based science case files, you can subscribe for more nights like this, one quiet mystery at a time. Back in my office, it's quiet. A small desk lamp pulls warm light across a folder with a simple label, The Big Bang. The folder doesn't promise fireworks, it promises measurements, old receipts, stamped and filed, and waiting for someone to read them in the right order. The room itself feels like a metaphor for the early universe, contained, dense with detail, full of motion you can't see directly. The air is warm near the radiator, cooler by the window. I can't see the currents, but I know they're there because a ribbon of steam from my mug rises, twists, and thins as it crosses invisible boundaries. That's how this case begins. Not with an explosion you could watch from a safe distance, but with a space that changes shape, and with light that keeps a record of the change. We can start with something simple and surprisingly soothing, a definition. Big Bang is a name we give to a model, a description of the universe's earliest hot, dense state, and its expansion from that state into the cooler, structured cosmos we live in now. It is not a claim that the universe exploded into empty space, like shrapnel into a silent room. It is not a movie scene with a center point and a spherical shockwave moving outward through pre-existing darkness. In the Big Bang picture, space itself is part of what evolves. The distances between galaxies grow. The wavelengths of light stretch. Time has a direction, and the universe cools as it expands. That cooling is not a side detail. It is the hinge that makes the whole story testable. If the early universe was hotter and denser, then it should have left behind very specific signatures. Signatures that do not depend on opinion or metaphor, or a narrator's mood. And those signatures are the spine of our case file. So tonight, we'll move through the evidence the way a careful investigator would. Not rushing towards the most dramatic moment, but letting each exhibit speak. First, the expansion itself, then the oldest light, then the first elements, and finally the long quiet interval when the universe had matter and light in principle, but no stars yet, no local lamps, only the memory of the earliest glow. I shift the folder closer, and the lamplight brightens the paper. On the first page, there is a simple idea with an almost unsettling calm. If the universe is expanding now, then it must have been smaller before. And if it was smaller, then everything in it was closer together and hotter and denser. This is not poetry. It is what happens when you wind the tape backward. Exhibit A is the expansion of the universe. If you point a spectrograph at distant galaxies, you find that their light is shifted toward longer wavelengths, toward the red. This redshift is not merely a Doppler effect in the everyday sense, like an ambulance siren changing pitch as it passes. In the cosmological picture, redshift is primarily a sign that space itself has stretched while the light was travelling. A photon leaves a distant galaxy with a certain wavelength. It crosses the universe for millions or billions of years. And during that travel, the universe expands. The space between wave crests grows, So the wavelength grows, so the light slides toward the red. This has a quiet elegance to it. Light becomes a messenger that cannot help but tell you how far it has travelled and how much the universe changed while it was on its way. In the office, I look at the blinds. Thin lines cut across the wall, parallel, evenly spaced. If I tilt my head, the spacing changes. The pattern stretches and compresses with perspective. It's a small domestic analogy, but it helps. If the scale of a room can change the spacing of shadows, then the scale of the universe can change the spacing of light's waves. Now, a single redshift measurement is interesting, but the case becomes convincing when you make many measurements across many galaxies and you see a pattern. The more distant a galaxy is, the larger its redshift tends to be. Distance and recession are linked. Not perfectly, because galaxies have their own local motions, like boats on a moving tide, but clearly enough that the overall expansion stands out. That link between distance and redshift is the kind of statement that sounds simple, right up until you ask the quiet follow-up question. How do we know the distances? In the office, it's easy. A few steps to the window, a few more to the door. The room gives you scale by habit, but the universe doesn't hand out rulers. So cosmology builds its distances the way a careful investigator builds a timeline, by layering methods, each one calibrated against the next, each one cross-checked where the overlap allows. It starts close to home, with geometry. Parallax is the cleanest kind of distance measurement. Watch a nearby star shift its apparent position against more distant background stars as Earth moves along its orbit. It's slow, patient geometry, but it anchors the bottom rung of the ladder. Then come the stars that help you measure farther out. Some stars pulse with a regular rhythm, brightening and dimming in a way that correlates with their true brightness. If you can determine a star's intrinsic brightness and compare it to how bright it appears, you can infer its distance. It's the universe offering you a standard lamp, one that needs careful calibration, but one that is repeatable. Once you can measure distances to nearby galaxies, you can begin to calibrate brighter beacons, events so luminous they can be seen across immense spans of space. Supernovae, the brilliant deaths of stars, become a kind of cosmic flare. Certain types, used with caution and corrections, behave like standardizable candles, not identical light bulbs, but lamps whose true brightness can be inferred well enough to turn apparent brightness into distance. This is how the distance ladder climbs: near, parallax; farther, pulsating stars; farther still, supernovae. And each rung matters, because the expansion story depends on both parts of the relationship: how fast something is receding and how far away it is. When those distances are in place, you can express expansion as a rate, how quickly space is stretching per unit distance. That number is often called the Hubble constant. It's a phrase that sounds final, like a verdict stamped in ink, but it behaves more like a measurement you keep refining. And from there, another quiet inference becomes possible. If the universe is expanding now, and if we can estimate how the expansion has behaved over time, we can estimate an age, an interval since the universe was in a much denser, hotter state. The age is not a single clue. It is a conclusion that must agree with other evidence. It has to sit comfortably beside the cosmic microwave background. It has to make room for the oldest stars. It has to match what we understand about how structure grows. This is one of the reasons the Big Bang case file feels unusually sturdy. It doesn't stand on one pillar. It's a vault with multiple locks, and they all have to turn. In my office, the desk lamp throws a steady circle of light onto the folder, and I think about how distance measurements work in practice, how they are never a single clean measurement, but a chain of careful steps, a ladder, a sequence, a quiet discipline. And once that discipline is in place, the redshift record becomes more than a curiosity. It becomes a timeline, because the farther you look, the earlier you see. The light doesn't arrive from far away so much as it arrives from long ago. And that means that expansion is not just something we measure today. It's something we can reconstruct across cosmic history, one careful rung at a time. And yet, even with a ladder, even with a timeline, there is a boundary to what any light-based investigation can show you. Not a wall you could touch, not an edge you could sail up to. A boundary made of time and transparency. In my office, the window is an honest boundary. It doesn't hide the city, it filters it. It turns distance into reflection and glare. It lets some light through and keeps some light out, and the shape of what I can see depends on the glass. The universe has boundaries like that too. The first one is simple. The universe has an age, and light travels at a finite speed. So there are regions so far away that their light hasn't had enough time to reach us yet. Even if those regions exist, even if they are full of galaxies, they are not part of our visible case file. Our evidence is limited to what lies inside our past light. Everything that has had time to send a signal that could arrive here. This is not a limitation of imagination, it's a limitation of causality. The universe tells you what it can. On the schedule, physics allows. And there's a second boundary that's quieter, but just as important. Even within the region whose light could, in principle, reach us, there were eras when light could not travel freely. In the earliest times, the universe was not like a clear night sky. It was like a room packed with moving bodies, photons scattering, charges everywhere, collisions constant. Light couldn't simply cross it and report what it saw. It was trapped in the crowd. So when we talk about looking back, what we really mean is this. We look back until we hit the first moment when light was allowed to move in long, uninterrupted paths. Before that, we can't use ordinary light as a witness. We have to rely on relics that survived in other ways. Elemental ratios, subtle patterns, the gravitational consequences of early conditions. It's like working a case where the security cameras only started recording halfway through the night. You still reconstruct what happened earlier, but you do it indirectly. From what changed, from what remained, from the marks left behind. This is one reason the Big Bang story feels both powerful and restrained. Powerful because we have multiple independent records that agree: expansion, an ancient thermal glow, and early chemistry. Restrained because we do not pretend the records exist where physics says they can't. Some pages of the universe's history are visible, some are readable only in summary, and some are still sealed, waiting for a better theory, or a new kind of measurement, or simply more time and ingenuity. When I return my gaze to the folder, that feels like the right posture for the whole investigation. Curious, but careful. Willing to follow the evidence all the way back to the oldest witness it allows. And willing to stop cleanly where the trail becomes inference rather than observation. Because a good case file doesn't fill gaps with drama. It labels the gaps. It tells you where the light can travel and where it couldn't. And then it keeps going, patiently, with the witnesses we do have. This is the observational backbone of the expanding universe. And it has a consequence. If the universe is expanding now, and if we roll time backward, there is a moment when everything we can see was closer together than it is now. The Big Bang model is not born from a taste for drama. It is born from the logic of expansion, paired with what else we observe. Because expansion by itself tells you smaller before. But to tell you hotter before, you need something more. You need a thermal clue. And the universe provides one in a form so steady and so patient that it can be easy to overlook. Exhibit B is the oldest light. In the earliest era of the universe, early in the sense of cosmic history, conditions were too hot for atoms to exist. When temperatures are extreme, electrons cannot settle into stable orbits around nuclei. Matter becomes a plasma, free electrons, nuclei, and a sea of photons. And in a plasma, light does not travel cleanly. Photons scatter off free electrons again and again, like someone trying to cross a crowded room while everyone keeps tapping their shoulder. The universe was opaque, not because it was filled with smoke, but because charged particles and light were intimately coupled. Then expansion did what it always does. It increased the volume, it reduced the density, it lowered the temperature, and eventually the universe cooled enough that electrons could combine with nuclei to form neutral atoms. This moment is called recombination. It is one of those scientific terms that sounds like paperwork, like an administrative process, but the physical meaning is vivid. Recombination is when the universe became transparent. With electrons bound into atoms, there were far fewer free charges to scatter photons. Light decoupled from matter and began to travel freely, in long, uninterrupted paths. Those photons have been travelling ever since. They have been stretched by the expansion of the universe, their wavelengths lengthened until they now appear as microwaves. And we can detect them from every direction. A faint, nearly perfect glow. This is the cosmic microwave background. If you want a single exhibit that feels like a signature across the page, this is the one. Because the cosmic microwave background is not just old light. It is old light with a particular kind of order. It has a spectrum that matches what you would expect from a hot, dense universe in near thermal equilibrium, radiation that once belonged to a unified, well-mixed environment. In other words, it looks like heat. Not heat you can feel on your skin, but heat that can be measured, plotted, and compared to a curve that physics already knows how to draw. That is the calm power of it. A thermal relic is hard to counterfeit. And then, once you accept that the cosmic microwave background is a relic from a time when the universe became transparent, you can do something even more revealing. You can look for the small departures from uniformity, the tiny temperature differences, the faint mottling. At first, it seems almost disappointing. So subtle you might miss it unless you're trained to look. But those tiny variations are the universe telling you where it was slightly denser, slightly hotter, slightly different. And those differences are not random noise. They have structure. They have a characteristic scale. They carry the fingerprints of processes that happened before the universe became transparent. One of the most soothing ways to imagine that structure is as sound. In the early plasma, before recombination, matter and radiation were coupled tightly. Gravity tried to pull matter inward, making overdense regions denser, but radiation pressure pushed back outward. That push and pull set up oscillations, compressions, and rarefactions, like sound waves, but sound waves travelling through a cosmic fluid of photons, electrons, and nuclei. These waves did not play forever. They were interrupted. When the universe became transparent at recombination, the photons stopped scattering and began to travel freely. The sound waves, in effect, froze into place. The pattern was captured. A final snapshot of where the compressions were, where the rarefactions were, and how far the waves had travelled before the curtain lifted. And the cosmic microwave background still carries that pattern. If you analyse the sky statistically, you can find a series of peaks in the power spectrum, features that correspond to those acoustic oscillations. This is one of those moments in cosmology that feels almost too neat to be real. But it is real, because it's measurable and because it matches a coherent physical story. Those peaks tell you about the contents of the early universe, how much ordinary matter there is, how much matter behaves as pressureless, dark matter, how radiation and gravity balanced, how the geometry of space looks on the largest scales. If you stay with that list for a moment, it starts to feel less like poetry and more like accounting. A cosmic ledger, not because the universe is bureaucratic, but because the evidence is structured in a way that lets you infer quantities you never measured directly. The peaks are not just bumps on a chart. They are a set of constraints. They tell you, in effect, how heavy the universe is in ordinary atoms compared to everything else that gravitates. They tell you how strongly matter and radiation were coupled before recombination, and how far a pressure wave could travel before the universe turned transparent. They tell you whether space is flat on the larger scales or curved, and how close it sits to that knife edge between the two. And once you have those constraints, you can do something that feels almost like reconstructing a crime scene from a single, perfect photograph. You can infer the universe's inventory, not item by item, but category by category. How much of the universe's gravitating content behaves like ordinary matter, stuff that can form atoms, stars, planets, and eventually paper folders on a desk? How much behaves like dark matter, matter that doesn't shine, but still builds scaffolding and deepens the wells? And how much behaves like something else again, an influence on expansion that becomes important later, when the universe is older and emptier? You don't need to pin exact numbers to feel the shape of the result. The result is that the universe appears to be mostly not ordinary in its mass-energy budget, even though everything we touch and see is made of ordinary matter. This is one of those quietly humbling outcomes that never asks for belief. It asks for attention, because it comes from independent clues that all point in the same direction. The cosmic microwave background provides one set of constraints. Large-scale structure provides another. Light element abundances provide another. And when they agree within the uncertainties, that agreement becomes part of the case. In my office, I think about how some investigations are solved not by one dramatic confession, but by a set of separate receipts that all match. The same date, the same amount, the same handwriting on the corner. Cosmology is like that at its best. A few separate records, written in different ink, all converging on the same account of a universe that expanded, cooled, and carried its early conditions forward like a watermark. And that's why those peaks matter. They're not just a pretty pattern, they're a way of turning the oldest light into a measured inventory of geometry, contents, and the early balance between pressure and gravity. And they do it with a kind of quiet clarity, because the early universe, for all its violence, had a simplicity. It was a hot plasma governed by well-understood physics, expanding according to gravity. There is also a related echo in the distribution of galaxies today. Those early sound waves set a preferred scale, an imprint that later appears as a subtle statistical feature in how galaxies are spaced. There's a name for that subtle feature in the galaxy map: baryon acoustic oscillations. It sounds technical, but the idea is gentle. In the early universe, sound waves moved through a hot plasma, compressions and rarefactions travelling outward from tiny overdensities. Matter wanted to fall in. Radiation pressure pushed out. So the universe rang in slow motion with a very specific note. When recombination happened and light decoupled, that ringing didn't vanish. It stopped evolving in the same way. The pattern froze, and what was once a moving wave became a preferred distance scale, a faint statistical bump that shows up later in where galaxies tend to appear, not as a visible ring around a single galaxy, not as a diagram you could point to on the night sky, but as a quiet tendency that emerges only when you count enough galaxies, across enough volume, with enough patience. This is the part that feels like surveying, like walking a coastline and measuring it by the rhythm of repeating landmarks instead of expecting one perfect ruler. Cosmologists take enormous maps of galaxies, three-dimensional catalogues built from redshifts and angles, and they look for that preferred separation. They compute correlation functions. They ask whether there is, in the statistics of where galaxies live, a slight excess at a particular distance. And when they find it, they treat it as a standard ruler, a cosmic yardstick. Because if you know the true physical size of that imprint, calibrated by the physics of the early universe and the CMB, then the apparent size of the imprint at different redshifts tells you about the geometry and expansion history of the universe. It's a clever trick, and it stays honest because it rests on the same early universe physics that produced the microwave background's peaks. The bell rings, once, early. The note gets recorded twice. Once in the oldest light, once in the later arrangement of matter. In my office, I think about a room that has its own preferred measurements: door widths, window heights, the distance between the desk and the wall. If you moved the walls outward while keeping the blueprint, the proportions would still be there, just scaled. Baryon acoustic oscillations are a little like that, a preferred spacing written into the blueprint early, then carried forward as the whole cosmic room expands. So when we talk about the universe keeping receipts, this is one of the cleanest receipts we have. A relic scale, a standard ruler, a way of turning the early universe sound into a measured distance in the late universe, quietly linking the first few 100,000 years to the galaxies we map today. It's as if the early universe struck a bell, and the note was recorded both in the oldest light and in the later arrangement of matter. This is why the Big Bang case file is so restful when you treat it as evidence. The early universe was not a black box that leaves no trace. It left a glow with a spectrum. It left a pattern with peaks. It left echoes that show up again, much later, in the structure of the cosmos. In my office, I think about the mug again. Not the steam this time, but the surface of the drink. If you tap the desk, the liquid trembles, making ripples that move outward, intersect, fade. If you froze the surface in an instant, you'd capture a pattern, a record of motion you can no longer see. The cosmic microwave background is that kind of record, a frozen ripple field, a gentle map of a universe that was once too hot and too dense to allow light to travel freely, and then, gradually, became transparent enough to let the oldest photons escape into the open. Seeds is a gentle word. It makes me think of dust motes floating in the lamplight, each one a tiny irregularity in an otherwise smooth air. But the scale is difficult to hold in the mind. Those tiny variations, small differences in the early universe's density and temperature, are where gravity would later begin its slow work. They are the first hints of where matter would gather and where it would be sparse. In a sense, the cosmic microwave background is the universe showing you its initial conditions, not at the beginning of time, but at the moment the universe became transparent. It is a photograph of the baby universe, a calm, full-sky image made of microwaves. If Exhibit B is the oldest light, Exhibit C is the oldest chemistry, because there is another way the universe keeps records. Atoms remember, not by nostalgia, but by ratios. The earliest minutes of the universe were hot enough for nuclear reactions, not the steady fusion inside stars, which depends on gravity compressing a core over millions of years, but rapid reactions driven by temperature and density in a universe that was cooling and expanding by the second. This era is called Big Bang nucleosynthesis. In the first few minutes, protons and neutrons collided and formed the lightest nuclei: hydrogen, helium, and small traces of lithium and beryllium. Then the universe expanded enough, cooled enough, that those reactions stopped. It's as if the universe ran a brief chemical experiment and then shut the lab down. And here is the forensic power of that. The outcome of that early experiment depends on the conditions at the time: the density of ordinary matter, the expansion rate, the balance between neutrons and protons. So if the Big Bang model is right, the universe should contain a characteristic abundance of these light elements. And it does. Hydrogen and helium dominate. The details are refined, argued over, measured with care. But the broad fact holds. The universe looks like it passed through an early, hot, dense phase that produced light elements in specific proportions. So now we have three pillars of evidence, three exhibits that reinforce each other. Expansion, old light, old elements, and they do something remarkable when you set them together. They let you build a timeline, not a timeline of certainty all the way to a mythical time zero, but a timeline of increasingly early conditions that are constrained by observations. I open the folder to a page marked with a thin pencil line, as if someone underlined it long ago and never erased it. After inflation stopped, it says, the energy transferred to matter and light, the Big Bang. That's a compact sentence for a very dense idea. So let's slow it down. The Big Bang model, as a modern scientific account, is usually paired with the idea of cosmic inflation, an early period of accelerated expansion that lasted a fraction of a second. Inflation is one of those concepts that can feel like science fiction if you meet it in a casual sentence, but it is motivated by puzzles that are, in their own way, simple. Why does the universe look so uniform on the largest scales? Why does it appear so close to flat, so close to having no overall curvature, when curvature tends to grow in many naive models? And how did the universe acquire the tiny initial irregularities that later grew into galaxies and clusters without being wildly chaotic? Inflation proposes that very early on, the universe underwent a burst of exponential expansion. A patch of space expanded so rapidly that regions which had once been in close contact became widely separated. That rapid expansion can explain the observed large-scale uniformity, and it naturally drives the universe towards spatial flatness. And crucially, inflation also provides a mechanism for creating primordial irregularities, tiny variations that begin as quantum fluctuations and are then stretched to cosmic scales, becoming the seeds for structure formation. This is why inflation is treated, by many cosmologists, not as decorative speculation, but as an explanatory framework. And yet, the file is honest. It notes what inflation does not solve. Scientists are not sure what came before inflation or what powered it. The Big Bang model, even with inflation, does not give a complete account of the beginning in the sense that philosophy might want. It gives an account of an early era, the earliest era for which we can build a consistent story constrained by measurements. This is an important tone to set, because the beginning of the universe is a magnet for certainty. People want a single sentence that closes the matter. They want a clean origin, like a birth certificate. Science is more like a trail of footprints, clear in some places, smudged in others, and absent where the ground was too hard, or the storm too strong, or the night too deep. So we will stay on the trail. After inflation, if inflation occurred, the energy associated with that era would have been converted into a hot mixture of particles and radiation. The universe would have been extremely hot, extremely dense, and expanding. At around 1 second after the Big Bang, according to NASA's overview, the universe consisted of an extremely hot primordial soup of light and particles. This is early enough that matter is not yet the familiar set of atoms and molecules. It is a plasma of fundamental constituents. A world where temperatures are so high that the distinctions we rely on in everyday life, solid and liquid, gas and vacuum, even atom and nucleus, are not yet available. In the office, I glance at the steam above my mug again. It's a poor stand-in, but it helps me keep the direction of the story. Steam rises, then spreads, and as it spreads, it cools. It becomes less visible. It fades into the air. Expansion is like that, in a cosmic sense. Spread out, cool down, become structured. In the earliest fractions of a second, the universe changed rapidly. But we don't need to flood the room with intimidating timescales. We only need to know the shape of the sequence. First, a universe dominated by radiation and fundamental particles. Then, cooling that allows protons and neutrons to form and persist. After that, we have a short window when those protons and neutrons can fuse into light nuclei. Then again, a long wait, hundreds of thousands of years, until electrons can bind to nuclei and atoms can exist. Followed by darkness, in the ordinary sense, because there are no stars yet. Until finally, we have the first stars, the first galaxies, and a gradual reionization of the hydrogen fog. This is the universe, learning to be visible. Let's take that sequence one room at a time. In the first seconds, the universe is dominated by radiation. Photons are abundant and energetic. Particles collide constantly. In such conditions, it is not helpful to imagine space as a quiet container in which matter sits. The energy density is so high that the geometry of space-time matters, and the expansion rate is part of the physics. As the universe expands and cools, quarks combine into protons and neutrons. Neutrinos, those nearly massless particles that rarely interact, stream through the hot plasma and eventually decouple, escaping into the cosmos in a background that is, in principle, still present, though extraordinarily difficult to detect directly. The universe, at this stage, is like a city at dawn, busy, loud, full of traffic, except the traffic is made of elementary particles, and the dawn is measured in seconds. In that city at dawn picture, there is a kind of traffic you can't really stop, and can barely even count. Neutrinos. They move through matter the way a rumour moves through a crowd, present everywhere, interacting only rarely, leaving little direct trace. In the early universe, neutrinos were part of the thermal bath, colliding and exchanging energy like everything else. But as expansion continued and the universe cooled, neutrinos decoupled. They stopped interacting often enough to stay in lockstep with the plasma. And once they decoupled, they became their own relic background, streaming freely through the cosmos, still present in principle, but extraordinarily difficult to detect in practice. This is one of the strangest features of the Big Bang story. The universe contains fossils that are not rocks, fossils that are not light, fossils that are particles moving through you right now without any interest in your existence. We don't rely on direct detection of the cosmic neutrino background to keep the case file standing, but we do have indirect ways to feel its presence. Because even when something doesn't interact much, it can still matter gravitationally. In the early universe, anything that contributes to the total energy density affects the expansion rate, and the expansion rate affects how long certain processes have to run, how the plasma oscillates, how nucleosynthesis proceeds, how structures begin their first slow steps. So neutrinos show up like an unseen hand on the clock, not in a dramatic shove, in a subtle change of timing, in how the early universe's rhythms fit together. Cosmologists sometimes summarize this with a simple question. How much radiation-like energy was present in the early universe beyond the photons we see as the microwave background? The answer is constrained by the same kinds of early universe observations we've been following, by the microwave background's patterns, and by the success of nucleosynthesis. The file doesn't pretend the neutrino relic is easy. It treats it the way it treats any hard-to-reach witness. It notes what can be inferred. It notes what remains beyond direct reach. And then it returns to the next strong, testable threshold. Because in the timeline, after the first seconds and the fast-moving traffic, the universe enters a brief but crucial laboratory phase. A phase where temperature and density allow protons and neutrons to build something more durable, nuclei. This is where the chemistry begins. This is where the universe starts leaving fingerprints that atoms will carry for billions of years. Then comes nucleosynthesis. In the following minutes, protons and neutrons collide and build light nuclei. Hydrogen nuclei, protons, are abundant. Helium forms. Traces of lithium and beryllium appear. There's a quiet footnote here that I like because it shows what hard science looks like when it's being honest. The light elements don't just support the Big Bang model, they also challenge it in small, precise ways. Hydrogen and helium fit beautifully into the story. Deuterium, measured carefully in the right places, also serves as a sensitive probe of early conditions. But lithium has a reputation for being a little stubborn. In some comparisons between the simplest Big Bang nucleosynthesis predictions and certain measurements of very old metal-poor stars, lithium can appear lower than expected. It's not a crack in the foundation. It's more like a smudge on one page of the file. And in good science, a smudge is useful. It means someone has to check the chain of custody. Are the stellar measurements reflecting the primordial abundance cleanly, or have stellar processes depleted lithium over time? Are there systematic uncertainties hiding in the analysis? Is the nuclear reaction network missing a small piece? Or is something slightly different in the early conditions than the simplest version assumes? I don't linger on lithium because it's sensational. I linger on it because it's instructive. It shows how cosmology works when it becomes precise. At first, you ask, does the broad story hold? Is there expansion? Is there an old thermal relic? Are light elements present in characteristic proportions? And once those answers are yes, you move to a more delicate kind of question. Do all the details agree? If one detail doesn't, is it telling you about astrophysics, about how stars behave, or about cosmology, about the early universe itself? The file stays calm here, because the Big Bang case is not built on one fragile number. It is built on multiple lines of evidence that reinforce each other. So a small tension doesn't collapse the story. It sharpens it. It reminds you that the universe isn't obligated to be simple, only consistent. And it reminds you that what we call the beginning is something we reconstruct from traces. Some of them pristine, some of them weathered, all of them worth reading carefully. Then, as expansion continues and the universe cools, the window for this kind of nuclear assembly closes. This is not a continuous process that lasts forever. It's a brief furnace phase that ends as the universe cools and the density drops. After that, the universe is mostly a plasma of electrons and nuclei for a long time. Light is trapped, scattering constantly. It takes hundreds of thousands of years for conditions to cool enough that electrons can bind to nuclei to form neutral atoms. This is recombination, and after recombination comes the release of the cosmic microwave background, the oldest light we can observe. This part of the story has a gentle clarity, because recombination is a threshold. Before it, the universe is opaque. After it, the universe is transparent. Before it, photons are constantly colliding and changing direction. After it, photons are free to travel. So when we observe the cosmic microwave background, we are not seeing the beginning in an absolute sense. We are seeing the earliest electromagnetic information that can reach us. We are seeing the universe's first clear light. And this light is not a featureless glow. It has texture, small variations, tiny temperature differences across the sky, anisotropies at the level of about 1 part in 100,000. Those variations matter because gravity is patient. Given time, small differences become large structures. Denser regions attract more matter, becoming denser still. Less dense regions become voids. What begins as a subtle pattern in the cosmic microwave background becomes the scaffolding of galaxies and clusters. In the office, the lamplight catches a speck of dust drifting slowly downward. It moves with no intention, following currents that are too faint to feel on the skin. And yet the speck's motion tells you the air is not still. The cosmic microwave background's anisotropies tell you the early universe was not perfectly smooth. It had the slight roughness required for structure. Now, if you look deeper into the cosmic microwave background, if you analyze the size and spacing of its features, you find hints of sound. Yes, sound. Not sound traveling through air, but pressure waves traveling through the early universe's plasma. Before recombination, photons and matter were coupled, and pressure could propagate through this mixture. These acoustic oscillations left an imprint in the pattern of the cosmic microwave background. They also left a related imprint in the distribution of matter on large scales, a preferred scale, like a faint ring in the statistics of galaxies. This is part of how cosmology becomes a precise science. It is not one observation in isolation. It is multiple independent lines of evidence that converge on the same story. A story of expansion, cooling, and the growth of structure from tiny initial irregularities. But perhaps the most sleep-friendly thing about this story is how it handles time. Because cosmic history is not a single dramatic instant. It is long intervals with different dominant processes. If you like, you can think of the universe as moving through phases the way a city moves through seasons. A hot, bright summer of radiation and plasma. A cooling autumn when atoms form and light escapes. A winter night, the dark ages, when there are no stars. And then spring, cosmic dawn, when the first stars ignite and the universe begins to change its appearance. After recombination, the universe enters the dark ages. The cosmic microwave background has been released. The universe is filled with neutral hydrogen and helium, but there are no stars yet to light the local sky. No galaxies, no familiar structures, just matter spread out and slowly gathering under gravity. This is an era that can feel empty in a documentary, but it is not empty in a physical sense. It is full of potential. The universe is still, in a way, but it is the stillness of a field before the first shoots appear. During these hundreds of millions of years, gravity works on the density variations seeded earlier. Dark matter, an invisible form of matter inferred from its gravitational effects, plays a central role in structure formation, providing gravitational wells into which ordinary matter can fall. That phrase, gravitational wells, can sound abstract until you sit with what it implies. It implies an architecture you cannot see directly, a scaffold that guides the visible universe into shape. In the case file, dark matter enters not as a mythic substance, but as an inference, an explanation for gravitational behavior that visible matter alone does not seem to account for. When galaxies spin, they do so at speeds that suggest there is more mass than the stars and gas can provide. When clusters of galaxies hold together, they do so with a gravity that appears stronger than the luminous matter would predict. When light from distant galaxies is bent and distorted as it passes massive structures, gravitational lensing, the amount of bending often indicates a mass distribution that extends beyond what we can see. Each of these observations is by itself a puzzle. Together, they point toward the same calm conclusion. There is a lot of matter in the universe that does not emit light the way normal atoms do. This invisible matter interacts gravitationally, shaping the growth of structure. And in the early universe, that shaping begins long before the first stars turn on. After recombination, ordinary matter becomes neutral and stops scattering light easily, but it is still pressured by temperature. It doesn't clump instantly. It has to cool and settle. Dark matter, if it behaves as we infer, cold, collisionless, largely interacting only through gravity, can begin to form clumps earlier. It begins to gather into a web of overdensities. Then ordinary matter falls into those wells. Gas drifts into the gravitational valleys. It compresses. It cools. It begins to form the first stars. This is not a dramatic assembly. It's slow. It's patient. It's gravity doing what gravity does, turning tiny differences into large structures, given enough time. When cosmologists simulate the growth of structure, starting from the tiny initial fluctuations implied by the cosmic microwave background, the results look eerily familiar. Filaments, nodes, voids, a cosmic web. Not a random spray of galaxies, but a large-scale pattern that reflects the universe's earliest conditions amplified by gravity. And this is another place where the case file feels unusually coherent. The same initial conditions that show up as tiny mottling in the cosmic microwave background can, under reasonable assumptions, grow into the broad structure we map in galaxies today. That doesn't mean every detail is solved. It means the big picture holds. In the office, there is an old radiator that clicks faintly now and then, expanding and contracting as heat moves through metal. Even a quiet room has structure. Warm zones and cool zones, currents and stillness, paths along which motion prefers to flow. The cosmic web is like that, on a scale that is almost insulting to the imagination. Matter does not spread evenly forever. It gathers along filaments. It leaves voids. It collects at nodes where clusters form. and those clusters become the largest gravitationally bound structures we can map. If you let yourself sit with the idea, there is something calming about it. The universe does not build everything at once. It builds from small variations. It builds through repeated processes. Gravity gathers, gas falls in, stars form. Stars die and return heavier elements to the gas. Galaxies merge and grow. Black holes accrete and influence their surroundings. The cosmos becomes layered. And all of it begins with those first faint differences, the ones that were already present, already encoded, already visible in the oldest light. Dark matter in this story is not a character in a myth. It is a name for the unseen mass that the evidence keeps pointing toward. A scaffold inferred from motion. A pressureless backbone that lets structure form efficiently. And like any good clue, it is powerful precisely because it shows up in multiple places at once. Rotation, clusters, lensing, and the large-scale pattern of the universe itself. The details of dark matter are still a mystery, but its gravitational influence is a strong part of the large-scale story we see. We can see the cosmic web today, filaments of galaxies, clusters, and voids mapped across immense volumes of space. Hubble has contributed to our understanding of this cosmic web and to the broader picture of cosmic expansion and its acceleration. But at this stage in the timeline, the Dark Ages, we are still before the first stars. What ends the Dark Ages is the first generation of stars. Theory suggests these first stars were unusually massive compared to the Sun, tens to hundreds of times the Sun's mass, and extremely bright. They burned fast, short lives on cosmic timescales. When they ignited, they did more than provide light. Their ultraviolet radiation began to ionize the neutral hydrogen around them. Hydrogen atoms, which had formed during recombination, were split back into electrons and protons. This is reionization. Not the first ionization, early on the universe was ionized already, but a second clearing driven by the first stars and galaxies. This is where modern observatories come in and where the story becomes gently contemporary. Hubble gave us deep fields, long exposures of tiny patches of sky that revealed thousands of faint galaxies, some of them extremely distant. Hubble helped refine the age of the universe with higher precision. It peered back in cosmic time to image some of the earliest galaxies, and it contributed to the Nobel Prize-winning discovery that the expansion of the universe is accelerating. And then there is Webb. Webb is built to see in infrared, which is not a stylistic choice. It is an answer to the physics of an expanding universe. Light from the first stars and galaxies began as ultraviolet and visible light. But as it traveled toward us across an expanding cosmos, its wavelength stretched. It was redshifted. For the most distant objects, that visible light is shifted into the near and mid-infrared. So to see the first galaxies, you need a powerful infrared telescope. Webb is able, according to NASA's description, to see back to about 100 million to 250 million years after the Big Bang. That is close, in cosmic terms, to the end of the Dark Ages and the beginning of cosmic dawn. It is a way of reaching into the era when the universe first became complicated. In the office, I turn the lamp slightly, and the shadow of the mug stretches across the desk. It is a simple geometry. Move the light, change the shadow. In cosmology, the geometry is grander, but the principle is similar. Change the scale of space, and the light changes on its way to you. The redshift is not just a curiosity, It is the reason cosmic archaeology is possible, because when you look far away, you are looking back in time. You are seeing galaxies as they were when their light left them long ago. You are not watching the universe as it is now, in some universal present. You are reading a layered archive, where distance corresponds to a deeper page in the book. And this is why the beginning of the universe can be studied at all. We cannot travel back. We cannot run an experiment that recreates the universe. But we can measure the relics. We can examine the oldest light. We can measure the light element abundances. We can map the large-scale structure. We can see how the expansion has behaved across cosmic time. And we can test whether these independent records agree on a consistent history. They do, within the uncertainties and the ongoing debates that sharpen the field. Now, there is a temptation to rush here, to sprint from the Big Bang straight to galaxies, to skip the slow parts. But the slow parts are where sleep lives. And they are also where the universe, in a sense, makes decisions. After the first stars, the universe does not simply become bright and stay bright. It becomes structured. Stars form in galaxies, and galaxies merge and grow. Black holes form and accrete. Gas cycles through generations of stars, and heavier elements, carbon, oxygen, silicon, iron, are forged in stellar interiors and dispersed by supernovae. The universe becomes chemically rich. It becomes capable of planets. And much later, in one quiet corner, it becomes capable of someone sitting at a desk and reading about it. But we are not obligated to race that far ahead. We can linger on what makes the Big Bang model compelling. Its ability to connect very different observations with one coherent thermal history. Expansion implies a denser past. A denser past implies a hotter past. A hotter past implies nuclear reactions early on, producing light elements. A hot, coupled plasma implies a time when light could not travel freely, followed by a moment when the universe became transparent, releasing the cosmic microwave background. And that background, with its black-body spectrum and tiny anisotropies, implies early conditions and seeds for structure. This is how the case holds together. Like a good file, it is not one dramatic clue. It is a stack of mutually reinforcing documents. Sometimes, when people ask about the beginning of the universe, what they really want is a verdict on the most mysterious part. What happened before the Big Bang? What caused it? Was there a first moment? In the file, these questions are set apart with a careful pencil bracket, not ignored, but handled with humility, because the earliest era is the hardest. There is a boundary of knowledge, and it is not a boundary imposed by lack of imagination. It is imposed by physics and observation. NASA's overview is blunt about this. Scientists aren't sure what came before inflation or what powered it. Hubble's page echoes the uncertainty. We do not know what triggered that initial rapid expansion, even if the inflation framework explains much of what we see. The MIT article, too, acknowledges that what happens before inflation is largely unknown. This is not a failure in the ordinary sense. It is the honest shape of the frontier. In physics, there are domains where our theories are extremely successful, where they predict, where they constrain, where they survive experiments. And there are domains where our theories collide, where the mathematics signals trouble, where we need a deeper framework. The beginning of the universe, in the sense of the very first instance, sits in that second category. General relativity describes gravity and the large-scale structure of space-time beautifully. Quantum theory describes the small-scale behavior of particles and fields with extraordinary precision. but to describe the earliest moments where densities and energies are extreme, we likely need a theory that unifies these frameworks, a quantum theory of gravity. We do not yet have a widely accepted, experimentally confirmed version of that theory, so the file stays careful. It tells you what is strongly supported, it tells you what is plausible, and it tells you what is unknown. This carefulness is part of what makes the story restful, because it means you do not have to hold everything. You do not have to force an answer. You can rest in the fact that the universe has given us real evidence and that science treats that evidence with respect. To keep our case file grounded, we can summarize what we know with the most reliable exhibits. The universe is expanding. The expansion leaves its imprint in redshift. The universe was once hot and dense. That early heat left a relic glow, the cosmic microwave background, the oldest light we can observe. The early conditions left a chemical fingerprint, light element abundances produced in a brief era of nucleosynthesis. Tiny initial variations exist in the cosmic microwave background and later grow into structure, forming the cosmic web. The universe had a dark age, and then it lit up with the first stars and galaxies. Reionization followed, a phase where neutral hydrogen was ionized by early luminous sources, and modern observatories, Hubble and Webb among them, are built to probe these eras and refine the story with better data. If you want a calmer way to hold that, you can think of the universe not as an explosion, but as an unfolding, a system evolving through thresholds, opaque to transparent, ionized to neutral to ionized again, smooth to structured, hot to cool. It's a story told in phase changes and imprints, and if the office is a metaphor for the early universe, then the metaphor works like this. At first, the room is crowded and loud in microscopic terms. Too many collisions, too much scattering, nothing travels cleanly. Then, slowly, the conditions change. Air clears, paths open, light moves farther without interruption. And once the room is transparent, even a faint glow becomes readable. The cosmic microwave background is that faint glow, the oldest light travelling freely once the universe became transparent. I take a slow breath, and the page in the folder barely lifts at the corner. A small draft, a small reminder that even in a quiet room, conditions change. In cosmology, the change is enormous, but the principle is still one of gentle continuity. Expansion is not a single shove. It is a long, persistent process. Even now, the universe continues to expand. And in the last few billion years, the expansion has been accelerating. This acceleration is inferred from observations that include distant supernovae and is part of the modern cosmological model. We often call the driver of this acceleration dark energy, which is a name for an observed effect more than a complete understanding. It is another place where science keeps the file open. There is, in other words, both closure and openness in this case. Closure in the sense that the Big Bang model is supported by multiple independent observations. Openness in the sense that some of the deepest questions remain unsettled. What powered inflation, if inflation occurred? What precisely is dark matter? What precisely is dark energy? How do we unify the laws we use so successfully in separate domains? And yet, none of that uncertainty changes the calm strength of what we do know. Because the universe has given us relics. It has given us a thermal afterglow. It has given us elemental ratios. It has given us patterns of structure. And it has given us, through redshift, a way to read distance as time. The file on my desk is not a myth. It is a carefully assembled story whose pages are made of measurements. A story that starts not with a bang you could hear, but with a glow you can still detect. And if you follow that glow backward patiently, it leads you to a universe that was once hot, dense, and young. It leads you to the earliest era we can describe with confidence. It leads you to the edge of what we can know. Outside, beyond the window, the sky is dark. Not the dark of the cosmic dark ages, not the dark of a universe without stars, but the familiar night above a city. Light pollution at the horizon, a few bright points visible where they can be. Still, I find myself thinking about the difference between darkness and emptiness. The early universe was not empty. It was not a void waiting to be filled. It was full, so full that light could not travel freely. And then it changed, and the light escaped, and the universe began its long drift toward structure. Tonight, we have followed the evidence gently. Expansion, old light, old elements, dark ages, first stars, first galaxies, Reionization, and the ongoing effort to refine what we know, with instruments designed to see farther and measure more precisely. I close the folder, not because the case is solved forever, but because the file is orderly. The evidence holds. The unknowns are labelled as unknowns, and the universe, for all its scale, feels like something you can sit with quietly, one calm detail at a time. The desk lamp glows. The mug has cooled. The steam is gone now, and the air in the office is still. But the story remains. A beginning told by what endured. A beginning written into the oldest light in the sky.